Plato Circuits Lab by Christian, Greg, and Jordan. So our goal was to determine the resistivity of a Plato circuit, and ours was shaped like an ice cream cone, and it was in 3 different pieces. It was in a cone piece, scoop piece, and cherry piece. So the equation for resistivity is resistivity equals resistance times cross-section area divided by length. And so to do this, to calculate this, we took measurements of the area and length of each component piece of the ice cream cone resistor, the length of each segment, the length of cone as a whole, and then we calculated the average cross-section area of the entire ice cream cone, and also calculate resistance by wiring it into a circuit with a fan, bulb, and other resistor. We measured the voltage and current across the bulb and used that with Ohm's law to calculate the resistance, which was 1,440 ohms, and the resistivity, which was 9.4 ohm meters. So, definition of terms, resistivity is an inherent constant to each material and measures its resisting power to electric current. 4 changes during our lab would affect resistivity calculation throw off our answers. If our area increased or moistness increased during the lab, the calculated resistivity would go up, and it would go down if the length of the resistor went up during the lab, and it would also be affected if the solder leads oxidized during the lab. So we took measures to counteract this. Resistance is opposition to current flow in a circuit. Current is flow of charge around a circuit, and voltage is difference between 2 different points in a circuit. Parallel wiring is making a circuit where the current can take 2 or more paths from junction point. So first in our step to calculate resistivity was calculating the average cross-sectional surface area. So for our cone component, the cone was a cone-shaped object, obviously. So we found the diameter halfway up the cone, and we used that to approximate a cylinder. So we found our radius, which was 1.25 centimeters, and then we used that to find the circular cross-sectional area, which was 4.91 times 10 to the negative 4th meters squared. For the cherry component, it was an approximate cylinder. So we found that the circular cross-sectional area was 1.77 times 10 to the negative 4th meters squared. And for the scoop of ice cream was also a cylinder, and its cross-sectional area was 0.00159 meters squared. So to calculate the average cross-sectional area of the total cones, including all its component pieces, we're taking the cross-sectional area of each component piece and multiplying that by a ratio of its length to the total length. And after doing that, we found that the average cross-sectional area of the entire cone can be modeled as 7.44 times 10 to the negative 4th meters squared. So the final piece was to find the resistance. And we had to do this experimentally and also be able to power a fan and a light bulb by creating a circuit. We then used our multimeter and a current across an ice cream resistor to find those 2 values and then plug it into Ohm's law to calculate resistance. So to control for the area and length of the resistor, we did not touch or alter the ice cream shape in any way. To control for voidness, we wiped our hands and limited touching of the ice cream resistor. To limit solder oxidation, we disconnected the current while not taking measurement. Then we wired in the multimeter on the branch with the ice cream cone to measure current, and also used the multimeter to measure the voltage across the ice cream resistor. So we wired the ice cream resistor on a path after the light bulb and in parallel with another resistor and the fan. So 2 batteries of 2.78 volts combined were used as the power source, and the resistor in the fan's path was integral to lighting the bulb, so we swapped it out many, many times before finally finding one that was low enough to power the bulb. And so in real life, our circuit looked as such. So this works because the Play-Doh is resistive, but not so much that it stops all current. Play-Doh conducts current due to it containing dissolved salt in water, but it also resists it a lot because it contains non-conductive elements dissolved in water, such as sugar. So the more Play-Doh, the more material the electrons tend to move through, so the higher the resistance. Since different pieces of Play-Doh stuck together, they function as a series of resistors. You can further simplify it to one resistor with the total resistance being the sum of the individual resistors' resistance values, as we have done. So when we measured the voltage across the ice cream resistor, we found that it was 0.95 volts. When we measured the current across, we found it was 0.66 milliamps. So then we took that voltage and divided it by the current in its path, in the ice cream circuit's path, and we found that the resistance was 1,440 ohms. To calculate the resistivity, we then took that resistance value, multiplied it by our average cross-sectional area of the resistor, and divided it by the total length of the ice cream resistor, and found it was 9.40 ohm meters was the resistivity. And in comparison to other resistors, it was way larger in size and length as comparison, and other resistors of similar resistance were smaller and more compact. Those resistors the actual resistors don't have any need for caution of oxidation of the solder. And it's a way higher resistivity than conductors like copper, but has way lower than common resistor materials like carbon. So So sources of errors include that the Play-Doh may not have been smooth on the inside. The different colored Play-Dohs likely had some difference in resistance, but we accounted for this by calculating the whole thing as a compound resistor. The depth of the solder going into the Play-Doh may have led to shorter, longer paths to the circuit. And the solder oxidized within the Play-Doh while the current was going through. We tried our best to control for this, but it still could have had an effect as the lab went on. The Play-Doh was likely not the perfect shape that we used for area calculations. The cherry especially got squished as trials moved on, and there were a limited number of trials. Ideally, you would do a few different Play-Doh ice cream cones to get a more accurate measurement.